Good morning. I just want to make a few announcements as I get started. The department is interested in doing a write-up about the robotics lab that you're all engaged in, and they want to send a photographer into the lab. And the times they're looking at are Tuesday, Wednesday, or Thursday between 3:35 and 5:30. That means it's these three slots. I assume you can see my cursor. Yeah, these three slots. So if any students who are doing their lab during these three lab periods object to having a photographer in there taking pictures, please let me know, and I will make sure that the photographer does not come into the lab during those times. If I don't hear from anyone, I am going to assume that you don't have any problems with it. Their job is not to ask you questions. Their job is to sort of blend in with the walls and just take pictures as you do whatever you're doing during the lab. But I do understand that it could be distracting, and so if anybody feels that they don't want to be distracted, please let me know, and I will make sure the photographer does not come to your session. I'm not sure which session they'll come in, but they did tell me it would be either Tuesday, Wednesday, or Thursday between 3:35 and 5:30 p.m. So if you're scheduled during those times and you have a problem, please email me. Let me know so we don't disturb you during your lab. This week started on the flashlight assembly, and by next week you'll be into the second week of that particular lab. Questions? Okay. Second thing is I again am going to meet with students today. Today is February 22nd, so I'll be meeting with these 6 students today. If you see your name there, please remember to join the office hours, and we've distributed in the past. There's the passcode that you can see in front of you to join the office hours meeting. From time to time, I have to text people to remind them, weren't you supposed to meet with me? Oh, I totally forgot. All right, so anyway, today from 10:10 till 1 o'clock, I'll be meeting with these students. There aren't many students left. I will be meeting with a few more students this coming Thursday, but I believe there's one student I haven't met with, and I haven't figured out who that is yet. So maybe this is a reminder to contact me, and we can work something out still. Okay, let me now, basically we're going to resume and talk about Jacobians. We're going to spend a lot of time talking about Jacobians, and we're going to talk about their application clearly and get into that, but we need to first figure out what does the Jacobian mean, what does it do, what is its significance, and how do we compute it. So I'm going to go through a series of explanations of what the components of each of the elements of a Jacobian looks like. And I'm going to do an example using one methodology, and I'm going to ask you to sort of take a look at a different methodology, which actually has been used in the last few exams for exam number 2. But I will lay out both of these so you can see them both, and there's no doubt that Robert Wagner will also be going over the Jacobian computation, and I've actually been talking to Nick Arswold, and he may also do a session on Jacobians somewhere along the way. And before I forget, The grades for exam number 1 will be distributed via Canvas this Wednesday evening. And Thursday morning at 8 o'clock, Robert will be going over the exam, and you'll have a chance to see the solutions of the exam on Thursday morning, this Thursday morning. All right, so let's begin. I started this the other day, and we're going to be looking at the Jacobian elements. Essentially, we have a robot, multiple degrees of freedom, multiple joints, starting with the base 0 sub 0, O sub 0, and there's x, y, z. We're going to have a revolute joint. And again, the base joint could be prismatic, and this is just arbitrary. We have a revolute joint in this particular case, in this direction, and there are joints, arbitrary joints, all over this robot going in every which way direction. And if I pick a particular joint, joint I think the important thing is to recognize no matter what kind of joint it is, whether it's a revolute joint or a prismatic joint, there's several identifying characteristics of that joint, which is basically related to how we do the DH, the Dennevet-Hartenberg convention. But at every joint, there's either going to be a revolute joint, in which case there's an angular velocity, theta sub I dot. Or if it's a prismatic joint, there's a d sub I dot. So either there's a prismatic linear velocity, which is directed along the z sub I minus 1 axis. Remember, z always, whether it's a revolute joint, it's about z sub I minus 1 for joint I. If it's a prismatic joint, it's essentially an extension along z sub I minus 1. So again, joint 1, joint 2, joint 3. So if I take joint 43 is with respect to z sub 42. And so there's the normal z-axis. And associated with each joint, there's a unit vector. The unit vector is always going to be pointing along the z-axis for that, the z sub I minus 1 for that joint. That's this unit vector B. So there are several characteristics at an arbitrary joint. There is a revolute joint has a joint velocity, a rotational velocity. A prismatic joint has a linear velocity, and they're acting along the normal for that particular joint. And then if we keep going all the way to the end point, this is basically where we're at. The whole point of the Jacobian is to determine what is the velocity, the derivative of the endpoint with respect to time. And the Jacobian is our way of figuring out in world coordinates and base coordinates the joint velocity, how is it related, not the joint velocity, the endpoint velocity, how is it related to the individual joint velocities? So that's the whole point behind what we're doing here. B sub I minus 1, the unit vector, and again I basically described this, but a very important vector which I want to point out to you is this vector r, and there is an r sub I minus 1, which is a vector pointing to the endpoint. Now, why is that vector important? Because we're going to have to do it. If it is a revolute joint, there's going to be a cross product involved in order to help us calculate the effect of the rotation, the effect of the rotational velocity of that joint on the translational motion of the endpoint. Okay? There is going to be an effect, and that effect is going to be a function of how far away the endpoint is from that joint. All right, and we're going to just break that down into elements as we move forward. The other day I laid out this result, and I've put this on the board a few different times, and today I'm going to do it again, but not on the board. Putting it on the board takes a lot of time, and I basically pre-wrote it out, and we'll take a look at it shortly. But before I do that, I just want to remind you that the velocity of that endpoint, again, notice these little zeros up on top, because we are calculating the velocity in the base coordinate frame. And so the velocity, that means the derivative of a vector. Remember, x is a vector. It's going to have three translational aspects to it. There's going to be an x component, a y component, and a z component. So this is the derivative with respect to time. And it is made up of the sum of the different effects. So there's going to be an effect of joint 1, and I'm using Q because I don't, when doing this analysis, we're doing it generically. That Q could be a revolute joint. It could be a prismatic joint. So we're just using a generic term Q. So again, the effect on the final x sub b with respect to time, there's going to be a component related to joint 1, and we're going to add on the component related to joint 2 and to joint 3 and so on. And then finally, for the nth joint, there's going to be the partial derivative of, again, the effect on x of that particular q sub n multiplied by the angular or translational velocity of joint n. So there are two kinds of joints. A prismatic joint is pretty straightforward. The prismatic joint effect on the final translational motion, it's just going to be the d sub I dot, whatever that linear velocity is, multiplied by a unit vector along the z-axis. So that's going to be essentially a fairly simple. This is if there is a translational velocity along this direction, its effect on x sub e is also going to be a translational velocity along the b unit vector. Okay? So there's no magic there. But if it's a revolute joint, it gets more complicated, because we have to recognize that when we are rotating a particular joint, it will have an effect on the translation of the endpoint. And so we need to remember that if there is an angular velocity over here, theta dot in this case, and so there's going to be an effect of this angular velocity vector, which is an effect over here, is basically theta dot, that's a scalar, multiplied by unit vector. This is going to be an angular velocity vector. And the final effect on E with respect to that particular joint is going to be the cross product of an angular velocity vector crossed with the vector, the distance off to that endpoint, which is r sub I minus 1. So it's the cross product of these two. So if I have two vectors and I take the cross product, I end up with a vector that's normal to the plane of the two vectors that are components of that cross product. So essentially, we can substitute for omega sub I here by theta dot times the b unit vector. And when we replace it, we get this equation where the scalars theta dot is brought out to the outside, and we're going to have a cross product between b sub I minus 1 cross product with r sub I minus 1. Remember, b is a unit vector. R is not a unit vector. That is magnitude. And when we take the cross product of that, we're going to get a vector that's normal to the plane between the b unit vector and the r unit vector. So for revolute joints, this becomes the component. And what I'm going to do is I'm going to write it out and go through some of the steps, because I want you to realize that even when we take a cross product, we're still going to have a 3/1 term that goes into the Jacobian. So let's write out, we're going to do a 3-jointed robot. And so I wrote out all the terms of the Jacobian for a 3/1. So just to remind you, we are always going to have 6 rows. Okay, the top 3 rows are going to give us the translation of x with respect to time. And I broke it up into an x component, a y component, and a z component. And the bottom 3 rows are going to be basically the derivative of the rotation, okay, at the endpoint, wherever my endpoint is, there's going to be also rotations about those 3 axes, and that's d phi e sub x, d phi e sub y, and d phi e sub z dt, and they're going to be equal to another set of elements. And notice there's a q1 dt. There's only 3 joints, so this is going to be a 3/1 vector. Those are the 3 joints. In world space, we always have 6 elements, and so the upper 3 and the lower 3. And what we're going to see is, because we have 3 joints, they're going to be 3 columns. And what we're going to do now is we're going to examine the upper 3 rows, because the lower 3 rows are going to be handled in a very different way. All right? We're going to make an assumption for the Jacobian that we're always dealing with very small changes in time increments. No matter what robot we're using, when we're talking about velocities, we're talking about breaking all the angles into very small differential changes. And we're going to see that when we do that, a lot of the terms, remember all these trigonometric terms that we do rotations about this and rotations about that, we have all sorts of sines and cosines show up. Well, we're going to see that when we're dealing with very small angular changes, a lot of the terms disappear. And we're going to simplify the lower 3 rows, so to speak, so that they're fairly simple and straightforward. The more complicated terms, and I'm not, complicated is all in the eyes of the beholder, the upper 3 rows are going to be fairly straightforward, and we're going to deal with each of them separately depending on if they're a revolute joint or a prismatic joint. And by the same token, depending if these are revolute joints or prismatic joints, we're going to plug in certain terms into the lower 9 elements of the Jacobian. Now keep in mind, if this was a 4-jointed robot, we'd have 4 columns. 8-jointed robot, there would be 8 columns. We're going to just stick to 3 joints in this particular case because the message is the same no matter how many joints we're dealing with. So let's consider the upper 3 rows first. And we're going to take a look at this prismatic joint, which I've already shown you this equation over here, which relates the motion at the endpoint with respect to a joint I. And we said if it's a prismatic joint, there's just a scalar d sub I along a unit vector B. And so if we plug in the terms, this is what it's going to look like. So essentially, this is the unit vector along the axis of that prismatic joint. Okay, that's the unit vector, and this is the velocity along that joint. This is for joint I. So this is joint 6. This was d sub 6, and this would be b sub 5 and the x component, b sub 5 the y component, and b sub 5 times the z component. So essentially, the elements of that particular column, the upper three elements, are basically going to simply be the unit vector along the z-axis of that joint. Okay? That unit, this is going to are the elements for a prismatic joint. Okay? So that's what we plug in, these three terms. If it is a revolute joint, it gets to be a little more complicated, but we'll see that it's a pretty straightforward formula. And we're going to use that formula we already showed for a revolute joint. The relationship is basically the cross product of the B unit vector, which is along the axis of rotation. It's along the axis of rotation, and it's going to be a cross product with the vector connecting that joint to the endpoint, which is this r sub I minus 1. So for a revolute joint, writing it out, we're going to have something that looks like this. And so we're going to have a cross product between the unit vector. It's going to be a cross product with the r vector. So if this is joint 4, this is going to be r sub 3, the x component, r sub 3, the y component, and r sub 3, the z component. And it's basically the vector which is going to connect from the joint to the endpoint. And we do the cross product, and when you do the cross product of two vectors, you get another vector, but it's still going to be a 3 by 1. So it's still going to fill in a column, which is a 3 by 1 column after you do the cross product. And that is going to be basically the three elements of the Jacobian for a revolute joint. So how do we determine this B unit vector? In a very straightforward way. And how do we calculate the r vector in a very straightforward way? Well, I just want to remind you that if you've calculated the A matrices for that particular robot, these are the A matrices that represent what is the 4 by 4 that takes us from the base coordinate frame. Notice I still have a 0 up here and a 0 and a 0. If we go from the base coordinate frame to joint 4, for example, okay, remember this is going to be A sub 3. This is essentially the product of a number of A matrices that take us from joint 1 to joint 2 to joint 3 to joint blah, blah, blah. Once we've multiplied all the A matrices to a particular joint, we're going to have a 4 by 4 matrix. And if we look at the components of that 4 by 4 matrix, the upper 3 by 3 is a rotation matrix, 3 by 3, and the upper right 3 by 1 is a translational vector. This x sub I minus 1 is basically going to be, that's going to tell us where this position is in world coordinates from the base. Okay? This 3 by 1 is telling us where we are over here. And this, remember what we said about this rotation matrix? The upper 3 of a 4 by 4 DH matrix is going to be the first column is the normal. It basically represents a coordinate frame where the first column represents the x coordinate frame, the second column represents the y coordinate, and the third column represents the z coordinate. We call them normal, orientation, and approach, but it doesn't matter what convention you use. This is going to be the unit vector pointing along x. This is the unit vector pointing along y. This is the unit vector pointing along z. So in essence, this tells us the origin of that particular coordinate frame, and this tells us the direction of the coordinate axis with respect to x sub I minus 1. You might call it O. you know, and in fact there are others who write conventions that they call this the O of the coordinate frame, the origin of the coordinate frame over here. I'm calling it X, but you can call it whatever you like. One of the things I want you to walk away from in this course is to recognize there's many different conventions, but they represent the same thing at the end. We might call them different names, but in effect, whenever we have a 4x4 homogeneous transformation matrix that meets all the conditions of a homogeneous transformation matrix, then the upper 3x3 on the left side are going to represent a rotation matrix of where the coordinate frame, and the upper right 3x1 is going to represent the position of the origin of that coordinate frame. So if we have these two terms, we have the unit vector at every joint calculated, and we know what the origin of this particular, where it is in world coordinates, that means where it is with respect to the base coordinate frame, then we can also calculate R, because R is a vector that connects the origin of that coordinate frame to the endpoint. So if I know where this is, and I know where this is, and I have vectors for those two, I can calculate the difference. And so what we're going to have is that the R, the vector that takes us, again, this is all in base coordinates, this means that this R vector, R sub I minus 1, is essentially equal to the endpoint's position, three components of this, y, x, y, and z. I'm sorry I call it x and the components are x, y, and z, but what can you do? This is a vector 3x1, which is telling us where the endpoint is. And this is a vector that's telling us where this is in world coordinates. If I subtract this vector, which is this vector here, from this vector, which is this vector over here, I am calculating the vector r sub I minus 1. What is the significance of this? Well, this makes it, if I know these and I know this, I can then plug them in to get the appropriate terms, because remember, I need to do a cross product. If I scoot back here, I need to do a cross product. So I'm basically showing you, if once I have the B unit vectors, which are these terms, and once I have these terms and these terms, I can calculate the R, and once I have the R, I can do the cross product and fill in the Jacobian elements. So that's pretty straightforward. Once we subtract these two, we get the components of R, and then essentially the components of R, these are the three components of the endpoint minus the three components of the origin of that particular coordinate frame at joint I. Once I subtract these two, I get R, and then you simply do the cross product, which is right here. And again, remember, the cross product is still going to be a 3x1 vector. So just reviewing very quickly, a prismatic joint, you basically plug in the B unit vector. And if it's a revolute joint, you have to calculate the A matrix. Once you've calculated the A matrix, you have the B unit vector, and you have the x sub I minus 1. You have to do a subtraction to get the R. Once you have the R, you basically plug in the cross product, and you then plug in the three terms of that column for the revolute joint. Okay? Those are the steps. So we've basically looked at calculating, if I go back, I'm sorry, I hope I'm not giving you whiplash here. We've basically determined how to calculate this column or this column or this column of 3x1s, depending on if it's a revolute joint or prismatic joint. Now we're going to take a step aside, and we're going to take a look at the lower 9 elements of the Jacobian. And again, if there were 5 joints, they would be 5 times 3, or 15 elements. But again, we're going to stick to 3 for right now. And so we're going to go through a complicated process here, step by step by step. But at the end, what we're going to find out is that the terms that plug in over here are really simple terms. Okay? They're going to end up being either unit vectors of that, the unit vector of B, or zeros. Okay? That's what we're going to end up with. So I'm giving you the end of the novel before I spend quite a bit of time on going through the steps to show you that that's valid. All right? So let's take a look at that. So we're going to look at the lower 3 rows of the Jacobian. And what we're going to be looking at is, let me just pick this up. What we're going to be looking at very specifically is we are now going to identify rotations about x, rotations about y, and rotations about z. Remember, we're now dealing with small rotations at the endpoint. So if I have a coordinate frame attached to the endpoint, and I want to have a very small rotation about x, which we're going to call d phi x, a small rotation about y by d phi y, and a small rotation about z by d phi z, we want to determine what we plug into the lower 3 by 3, in our case, of the Jacobian. And what we're going to do is we're going to show that they behave like a vector. When we're dealing with very small rotational changes about x or y or z, we're going to see they have the properties of a vector. The properties of a vector that are important in our particular case is order doesn't matter. Remember what we said before when we move and we shift coordinate frames and we first rotate about x and then rotate about y and then rotate about z. That is not the same as first rotating about y, then about z, and then by x. But when we're dealing with very small angles, yes, it doesn't matter what the order is, and I'm going to show that. And the other thing we're going to show is if we consider these properties, it turns out we can add them. You know, when you add 2 vectors, you get a third vector. We're going to show that we can add these differential terms, and you just add the components and you get the final result, which is rather unique. But it does apply in this case because remember, d phi x, d phi y, and d phi z are very small. And keep in mind, what does that mean? That if I take the sine or the cosine of very small angles, what happens to those very small angles? We're going to see that if I take the cosine of a very small angle in radians, then the cosine of that small angle is 1. And if I take the sine of a very small angle in radians, and that small angle is, let's say, d phi x, the sine of d phi x is d phi x. Okay, you can plug that into your calculator and try that if you don't remember. But the bottom line is if I have a 3 by 3 rotation matrix, this is a rotation by a small d phi x about x. This is what the rotation matrix looks like. Cosine minus sine, sine, cosine. And we're going to look at very small d phi x. That means way smaller than 1. And again, we're dealing in radians. This is what the 3 by 3 matrix ends up looking like. And so here is d phi x. This is a rotation about x by d phi x. This is a rotation about y by d phi y. And what we're now going to do is we're going to multiply these two matrices. We're going to multiply one 3 by 3 matrix by another 3 by 3, and we're going to get a 3 by 3 matrix outcome. But notice the important thing that happens when I do this multiplication, and I'm not going to spend time on doing the multiply, I just wrote it out over here. Notice that when we have a very small number, in 0.01 times 0.01 is going to be 0.0001. So we're talking about when you take the product of very small numbers, you're going to get something that we're going to approximate as 0. So notice when I had d phi x times d phi y, I'm going to call that 0. And so when I take a rotation about x multiplied by a rotation about y, by d phi x and d phi y, I'm going to get a result that basically says I have, along the diagonal, I have 1s. I'm going to have a d phi y up here, a minus d phi y here, d phi x and minus d phi y. And notice if I did the same thing, but did a rotation about y, this is what I would get if I did a product of first a rotation about y, then a rotation about x. And I carried it out, I got this 3 by 3. Then this term would go to 0. And if this term goes to 0, notice that this expression is essentially the same whether I'm multiplying first by x, then by y, or first by y, then by x. Order no longer matters, so we call that commutative, and that's one important property of vectors. So it behaves like a vector. All right, wonderful. But keep in mind, we're talking about very small angular changes. The whole notion of Jacobians is, it's critical to remember we're dealing with small incremental changes so that we can make this kind of an assumption. And now we're going to take a look at a different element. We're basically going to say that this behaves like a vector, this d phi, and it's going to have a component d phi x, d phi y, and d phi z. Remember what those are. Those are small rotational changes about x, small rotational changes about y, small rotational changes about z. These are not 50 degrees, 30 degrees, 10 degrees. We're talking about very small numbers, fractions of a degree. And so this is a 3 by 1. And so let's take a look. If I basically take, notice this element, this is the product of rotation first about x, then a rotation about y, and then a rotation about z. This is what it looks like. If I plug in all the terms and get rid of all the second order terms, I'm going to get this expression. And that's true whether I do ry times rz times rx or rx times y times z. It doesn't matter what the order is. We're always going to get this 3 by 3 matrix, a 3 by 3 matrix. And now what I'm going to show you is that if I have two small sets of rotations, so if I have, first I'm going to do a rotation by a very small angle vector 3 by 1 of d phi 1. And then I'm going to consecutively multiply, and I'm going to take a look at d phi 2. And again, we're talking about their very small rotations. I'm going to basically have this 3 by 3 is going to look like this. Notice the components are z sub 1, y sub 1, x sub 1. Just plug them in over here, I get this. And this is going to be the second 3 by 3. Notice I've changed everything. Here it's sub z sub 2, sub y sub 2, sub x sub 2. If I take this 3 by 3, multiply it by this 3 by 3, I'm going to get a 3 by 3. But notice what happens. I'm getting rid of all the second order terms. Anytime I have the product of two small angles, I say they're equivalent to 0. And then notice what happens. then when I take the product of these two 3 by 3 matrices, notice what happens to the components of this 3 by 3. Each of the elements, where before it was d phi z sub 1, it's now the sum of d phi z plus 1 plus the sum of d phi z2. Here it's the sum of d phi z1 and d phi z2. So what's happening is when I take two small orientational changes, I have a very small rotation about x, small about y, small about z. And then I do another small rotation of x, y, and z consecutively. It's as if I just did one rotation of the sum of each of those two small rotational changes. And so what we're basically saying that in effect, it doing two consecutive small rotational changes is the equivalent of basically adding the components, which again makes this behave like a vector. When I take two vectors, one of the properties of a vector is if I add vector 1 plus vector 2, in effect we can sum the components of those two vectors, and we're going to end up with the same, we're going to end up with the result. So that means they behave like a vector. We can treat them like vectors, and that's what we're going to end up doing to basically simplify a lot of the results in the Jacobian. I just want to take you back for something and just remind you. If we take a look, now I'm going to basically do very simple large rotations. If I start off, here's x, here's y, and here's z. And I'm going to now rotate, and I'm going to rotate along the x-axis by 90 degrees or pi over 2, and 0 along the x and 0 along the y. So just let's take a look at this, this particular case. Here's where I start off with x. I'm going to rotate by 90 degrees. So this y is going to move up this way. Z is going to move down. So I'm going to end up with this coordinate frame. Then I'm going to rotate. I'm going to take this coordinate frame, and I'm going to say I now want to rotate it by about y by 90 degrees, but nothing about x and nothing about z. So here, again, use my right-hand rule, stick my right thumb up along y. I'm going to rotate about y by 90 degrees. Z is going to move to where x was, and x is going to move over here. We're going to end up with this coordinate frame. So if I have two coordinate frames, one coordinate frame, and I process them first about a rotation about the x-axis by a large angle, and then about the y-axis by a large angle, I'm going to get this result. And if I now reverse the situation, I first rotate about 90 degrees, okay? And this time I'm rotating about y. If I rotate about y, again, z moves down, x moves down. I'm going to get this coordinate frame. And now I'm going to rotate about 90 degrees about the x-axis. Again, put my right thumb down along x. When I do that rotation, z is going to move this way and y is going to move this way. Notice this coordinate frame, these two coordinate frames are not equal to each other. So when we're dealing with large rotations, and by the way, large could be 5 degrees. When we're dealing with larger rotations, order matters big time. But when we're dealing with fractions of a degree, order no longer matters. Okay? And that's an important takeaway from all this. And that is why we're going to be able to do some very simple things. If we're looking at the lower 3 by 3 terms, okay? Let's go back and just refresh your memory what I'm talking about. Sorry that I'm swinging all the way up here. Okay, we're now looking at these, the lower 3 by 3 elements. Essentially, what we're saying is we can look at these as vectors, but what is the net result of all that? Well, the net result of all that, sorry for bouncing around, go down here. Essentially what we're saying if there is small orientational changes at the end effector, small orientational changes, those small orientational changes are equivalent to simply whatever's going on in the revolute joint at that particular joint. It's also occurring at the end effector. So if there is a theta sub I dot multiplied by unit vector at a revolute joint anywhere in that manipulator, that is shifted over to where the end effector is in space. And we're also saying that if there is a prismatic joint anywhere, it has no effect on the orientational changes at the end effector. So for a prismatic joint, the 3×1 is going to be simply 0 as the 3×1 elements of the Jacobian. And if there's a revolute joint, whatever took place at that particular joint, that is going to have effect on the endpoint. Okay? And it doesn't matter what's going on in the rest of the robot. All right? So in effect, we end up with very simple elements in the lower 3 in our case for a 3-jointed machine, 3×3. So to summarize, if I basically create and I merge the translation and rotation into one, so essentially the upper 3 is the differential change of x, the small translational motions x, y, and z at the end effector, and d phi e are the small orientational changes about x, y, and z. Then the Jacobian is going to be made up of columns, and they're going to be n columns depending on how many joints. In our analysis, that was 3. And essentially, each column is either going to be, if it is a prismatic joint, the upper 3 is going to be the unit vector b, and the lower 3 is 0. And if it's a revolute joint, the upper 3 is the cross product of the b unit vector with r that we discussed. And the lower 3 is going to be just the unit vector of that particular joint. So using these results, we can essentially plug in all the columns of a Jacobian, whether it's 4 columns, 5 columns, 6 columns, depending on how many joints we have. Any questions? We're basically looking at dp. We're calling dp this merging of the 3×1, which is the small differential changes of the end effector, and d phi e, small differential changes, joint rotations about the end effector. We're calling that d phi e. So this is kind of the combination, and we're putting a dp out there, and we're going to see later that there's applications of this in a variety of different situations, which we haven't talked about yet. But this Jacobian has other applications we haven't talked about, and that's why we're spending as much time as we are on this idea of a Jacobian. Questions? We're going to work through an example. And this example is a 3-jointed robot. And I am not going to use those A matrices that I talked about. I'm going to just use basic trigonometry to do all the calculations of the unit vectors and calculate the r vectors and plug everything in to get a result for the Jacobian. You, as an exercise to sort of figure things out, I suggest you work out the A matrices for this particular robot. And given the A matrices, you will get the B unit vectors, you're going to get the R vectors, and then plug them into the cross products and everything else and work out the Jacobians. I'm going to go through this and end up, this is what the 6×3 or 3×6 Jacobian looks like for this particular robot. And we're just going to step through this very slowly. because I want you to understand what all the elements mean and their significance. And I think you have a much better perspective than simply plugging in A matrices. Because when you do A matrices, number one, making one small mistake in a product will give you some bad results. Obviously, you can make small mistakes here too. But I just want you to see where all the unit vectors are. And I'm going to do, there are going to be two revolutes joint 1 and joint 2. And joint 3 is going to be a prismatic joint. And so we're going to go through this analysis. And I'm going to just show you where all the unit vectors are and where all the magnitudes are. And we're going to just review all this and take our time doing it so that you see all the pieces and how they come together. So let me first start off by identifying what this robot looks like, where the revolute joints are. And when I did this initially, I recognized afterwards it's sometimes hard to see that this is O sub 1. And so I basically, this is O sub 0 over here. This is O sub 1. And there is O sub 2. So this time I added some red arrows to capture your attention of where they are. And notice the two revolute joints. The first revolute joint, there is theta 1. Okay? And theta 1 is rotating about Z0. Z0 is straight up over here. There's Z0. It's rotating about Z0. So there's theta 1. There's X sub naught. And there's Y sub naught. Okay? The next joint is also a revolute joint. But it's off from the base. It's at a distance from the plane of X, O, Y by a distance L sub naught. Okay? So it's up here. And essentially, I picked the revolute joint intentionally to be 90 degrees offset. So when theta 1 is equal to 0, where would B1 be pointing? Anyone take a look at it and just tell me where they think B1 will be pointing when theta 1 is 0. This time I'm going to let you think about it and struggle a little bit. Where would theta 1 be pointing? Notice I'm drawing B1 over here. B1 is the unit vector along this revolute joint. It's the revolute joint, which is now, here's O1. And it's, again, rotating along B. And the B1 is essentially identifying the Z sub 1, so to speak. But where is it with respect to my base coordinate frame? When theta 1 is 0, this line comes back to be pointing to O sub 0, X sub 0. So where is B1 pointing? It's pointing in the Y direction. Okay? It's then going to be pointing in the Y direction. So when theta 1 is 0, B1 is pointing in the Y direction. Okay? That's an important takeaway. So B sub 0 is going to be 0, 0, 1 because it's pointing in the Z naught direction. So that's why there's a 1 here. But B1 dot is going to have 3 components to it. All right? I think you should immediately recognize that it has going to have a 0 for the Z component. Right? It's essentially going to be, it's going to always be operating in the plane, in the XOY plane. So the Z component is always going to be 0. But what are the cosine and sine components of B1? Well, essentially, as I rotate theta 1, there's going to be a an x component, which is going to be the cosine of theta 1, there's theta 1, plus 90 degrees. Because remember, when theta 1 is 0, B1 is pointing in the y direction. And as theta 1 grows, okay, that 90 degrees is also going to move. So essentially, the x component is going to be the cosine, all right? It's going to be the cosine of theta 1 plus pi over 2. That's this term. And the y component is going to be the sine of theta 1 plus 90 degrees. Before we go on, is that clear? Okay, because the next B2 is going to use that result. So essentially, this is the x component of B1, this is the y component of B1, and there's the z component of B1. It's a unit vector, which is a function of theta 1, and there's that 90-degree offset. Because if you take a look, go look at the textbook, every example they give, they never give you anything very complicated. So I thought I'd throw in this 90 degrees here to be different, okay? Because otherwise you think all of them don't have this 90 degrees. It really depends on where you put that revolute joint. And in this case, the revolute joint is identified to be off from the original, to be pointing in the y direction. Okay? It could be pointing in other directions. It could be pointing in 45-degree angle. There's nothing magic about 90 degrees. It's just, I picked it since it's easy to do the cosines and sines. And in fact, right here, whenever you have the cosine of an angle plus 90 degrees, it's the same as minus sine of the angle. And whenever you have the sine of an angle plus 90, it's the same as cosine of the angle. Okay? So B1 is, again, a very simple 3x1 unit vector. No magnitude. Now what about B2? B2 gets a little complicated, and you're going to have to sort of have some patience here as we do B2. B2 is a unit vector. This is a prismatic joint. And so I am now, remember, the first was a revolute joint, the second was a revolute joint, and they intersect in this particular point. Theta 2 is the angle, remember this is joint angle 2, which is an angle about B1. Okay, remember? Joint angle 2 is a rotation about B1. That means it's coming from up here going down. Okay, and this is in the plane normal to the B1 unit vector. You see that? I know sometimes it's hard to see depth in a two-dimensional screen. But in effect, just basically what I'm saying is that this vector from O sub 1 up to O sub 3. Now, O sub 3 is where the endpoint E is. Okay? This is the endpoint. We have a prismatic joint. That means that from O sub 2 to O sub 3, it's going to move up and down depending on the value of D3. D3 is the displacement of that prismatic joint. So as that prismatic joint, as E moves further away from O1, D3 is going to get larger. As E moves closer to O1, D3 gets smaller. So D3 is the displacement along the B2 unit vector. The B2 unit vector is the unit vector along which you have translation. Okay, you have translation along here, and it's going to be moving up and down depending on the value of D3. And what is important, of course, is the whole point behind the Jacobian is we're trying to calculate what is the velocity of E in world coordinates as a function of the three components, which is, what if there's a theta 1 dot, a theta 2 dot, and a d3 dot? Each of those three joints are moving at some velocity, and we want to calculate, well, what effect does that have on the velocity of E along x, E along y, E along z, and the coordinate frames, the rotation about the local x, the rotation about local y, the rotation about local z. So far, now let's try. We still haven't calculated the B2 unit vector. And I notice that it's now 9 o'clock. And well, I think it's best to, let's take a break right now. We'll take a 10-minute break. And then we'll resume this analysis after the 10-minute break. Okay? Thank you. So I can get your attention back. So clear your brains from whatever you were looking at. And let's get back to this particular problem. Again, just to remind you, we have two revolute joints and one prismatic joint. First revolute joint is rotating about B sub 0, which is pointing straight up. The second rotational joint is rotation about B1, the unit vector, and that's a unit vector that's always sitting in the xy, xoy plane. Okay, so there's this B1 which can rotate around, and we just finished discussing and describing that that unit vector B1 is going to depend on theta 1 because it's 90 degrees offset from the original x or y coordinate frame. And so the unit vector B1 looks like this. Now let's take a look at the B2 unit vector, which is a little more complicated, and you're going to have to put your three-dimensional visualization brains, turn them on, to see this. So first of all, remember what we're trying to do. We're trying to calculate the three terms, a term in the x direction, y direction, and z direction of where this B2 is pointing. So imagine for a moment that wherever it's pointing up here, it's going to be pointing based on the value of theta 2. And theta 2 is an offset from the vertical. Okay? It doesn't matter which way. It's an angular rotation about the B1 vector, and so it's an offset in this direction. So let's for a moment think that this vector O sub 1 to E, if we basically project it down into the XOY plane, we're going to get this little solid line over here. This solid line is a projection of this vector into the XOY plane. Okay, so let's think for a moment what that is going to do, because what that's telling us is the x component and the y component is going to be a function of theta 1. It's going to be, remember, this is a projection into the XOY plane. And so the x component is essentially going to depend on the value of theta 1. And so the x component is basically going to be the cosine of theta 1 in this direction. And the sine component is going to be the sine in this direction. So essentially the two components of the projection, remember this is the projection into the XOY plane, is going to be cosine of theta 1 and sine of theta 1. But keep in mind they're going to, remember this B2 is up here. And so it is essentially going to be, it's going to be a function of theta 2. Depending on theta 2, remember theta 2 is over here. So if I take a look at the sine of theta 2, okay, let's think for a moment what that means. If I create a right triangle here, so I'm going up in this direction, and I connect it up to this E, basically the sine of theta 2 is going to tell me what the offset is in that direction. So it's basically going to be the x component is going to depend on theta 1. So there's cosine of theta 1. But then it's going to multiply by the sine of theta 2, which is going to tell me how much this E sticks out away from the z-naught axis. So it's going to be all the way over here, but it's going to have two components. There's the component of theta 1, which is going to kick me out here to this projection. And then there's going to be the component of theta 2, and it's going to be the product of cosine theta 1 times sine of theta 2. The y component is going to be the sine of theta 1, which is essentially in the y direction component of this element here. Okay, think of this as a hypotenuse in sense. And we're going to multiply that by the sine. We're going to basically get the cosine of theta 1 times sine of theta 2. The sine of theta 1 times sine of theta 2. Still this component over here. But the z component is going to be the cosine of theta 2. The cosine of theta 2 is going to tell us how far off the z axis it's going to be. So essentially, the cosine theta 2 is going to tell us how far is E. If this is my E over here, essentially, that theta 2, the larger theta 2 is, the smaller the z component. The smaller theta 2 is, I'm going to be the larger the z component. Okay? Remember, the z component is going to move up and down, and the z component, when the theta 2 is small, it's going to have large, and then it's going to drop down. When theta 2 is large, the z component is going to get small. And so in effect, this is the z component. It's only a function of theta 2. But the x and y components are a function of both theta 1 and functions of theta 2. So essentially, this is the unit vector B. Now, again, I'm using trigonometry to do all of this. And if we have a complicated robot, I can tell you right now, the A matrix is always the way to go. Compute the A matrix. You have a standard process for calculating each of the A matrices. And by looking at each A matrix, you will know where the B unit, what the unit vectors are, and the position of the coordinates. All right, so we've calculated 3 unit vectors. Now we have to calculate the 2 r vectors. Let's go back and quickly take a look at what those r vectors are. Sorry for all the whiplash here. But the r unit vector, it's not a unit vector, I'm sorry. The r vector is from the joint of interest, joint I, to the endpoint. That's what the r vector. It's the distance from the origin of that joint to the endpoint. Okay, so for r0, it essentially is going to be from the very first joint to the endpoint. And for r2 and 3 and 4, it will essentially be vectors. So if we go back down, sorry for doing this. Essentially, R1 is going to basically be, it's going to be from joint 1 to E. So that's joint 1 over here. And it's going to be going from here out to here. So it's going to be the distance d3 times the unit vector b2. That's the vector from here. Because this is a prismatic joint, it's simply going to be the distance d3 times the unit vector along which is traveling. That's what r1 is, because we're going from the r1 joint. From the r0 joint, which is down here, the r vector is going to go from here all the way up to E, which is over here. Well, that vector is simply going to be the sum of L0 times B0, which is going to take us from here up to here, plus D3 times B2, that gets us to here. So essentially, the vector R0, which is the vector that connects O sub 0 all the way up to E, that's this vector over here. It's the sum of the vector going up to this location, which is L. That's the distance L sub 0 times the unit vector B sub 0, plus D3 B2. This term is the same as this term over here. So this is from joint 1 to E, and this is from joint 0 to E. Those are the 2 R vectors. And now we can plug them in order to figure out what the terms are. Remember what we're doing. We're taking the partial derivative of E, which again, it has 3 components. And we're taking the partial with respect to the first joint, joint 1. And we've basically said this is a revolute joint. So it's basically going to be equal to theta 1 dot times the cross product of B sub 0 crossed with R sub 0. Okay, so it's B sub 0 is this term up here. That's this term here. It's just a very simple 0, 0, 1. But it's a crossed with R sub 0, which we said is L sub 0 times B sub 0 plus D sub 3 times B sub 2. So when we're doing a cross product of this expression, we basically do the cross product of each of the two of them. The cross product of a vector crossed with itself is 0. Okay? So the cross product of B sub 0 with this component, it just disappears. And so we're simply going to have the cross product of basically D3 B0. We pull out the D3, which is over here. And it's going to be the cross product of B0, which is right here, crossed with B2. So the cross product of B0 crossed with B2. There's D3, which is the value of the displacement at that particular point. And it's going to be multiplied by the joint velocity theta 1. So theta 1 dot. So be careful. This is a dot, not a little 0. I'm sorry for the potential confusion. But this is theta. This is the derivative of theta 1 with respect to time. D3 is, at that instant time, D3 is a constant. And we're doing the cross product of B sub 0 crossed with B sub 2. So if we take the cross product, essentially we are going to get, and remember when you take a cross product, this is a simplified version of a cross product. You're going to essentially take the magnitude of vector A, the magnitude of vector B multiplied by the sine of the angle. And again, remember the cross product is always normal to the plane of A and B. But when we do that, we are going to effectively get, this is going to be minus S1 times S2. This is going to be C1 times S2. And this is going to be 0 over here. So there's no motion in the z direction. But there is going to be, when we do the cross product of B sub 0, which is this very simple expression, which with B2, which is this expression, we're essentially going to get this column over here. This is going to be the first column. And what are we talking about? This is the Jacobian. Here it is, minus D3 S1 S2 plus D3 C1 S2 and 0. Those are these three elements in that first column. So this is the first column over here. D3 minus S1 S2, D3 C1 S2, 0. Then if we do the next element, this is going to be theta 2 dot. This time it's B1 crossed with R1. R1 is D3 B2. That's a unit vector. So this is D3 B2. That's this expression. We cross it with B, the unit vector B1, which is this term over here. When you take that cross product, you get this expression. And this expression is going to be the second column over here. D3 C1 C2, D3 S1 C2, D3 S2, minus D3 S2, that's over here. There's the D3, D3 C1, D3 C S1, D3 minus S2. And then when we take the third partial derivative of x with respect to the third joint, remember which is a prismatic joint. Because it's a prismatic joint, in this particular case, here it is, it's simply going to be the unit vector B2, which we've calculated up here. That's this vector over here, multiplied by D3 dot. So we get this. This expression is going to be the third column, which is over here. So those are the first three columns for those joints. And what are the bottom three columns from the joints? Remember, when we're dealing with the bottom three columns, if it's a revolute joint, we just plug in the unit vector for that revolute joint. In this case, B, the unit vector B sub 0. The second one is b sub 1. And so that's going to be 0, 0, 1 for the first one. The second unit vector is going to be this term over here, which is over here. And the third is a prismatic joint. And if it's a prismatic joint, that's simply 3 zeros. And they're plugged in over here. Now let's just look at this Jacobian for a moment and see if there's any takeaways in this Jacobian. And I think I want to point out, and I'm going to emphasize this as we do other problems later on, the elements of the Jacobian are at an instant in time. The Jacobian changes as the robot moves around in space. And at each position in world space, we're going to evaluate a different Jacobian. Jacobian is not a constant. Notice, look at it. These elements here are a function of what D3 is. D3 has a value at a certain point in time. Theta 1 has a value at a certain point in time, and theta 2 has a value at a certain point in time. So at that particular point in time, we know what theta 1 is, we know what theta 2 is, we know what D3 is, and so we calculate the Jacobian. That means that our robot moving around in space, remember this is telling us how fast it's moving around in space at an instant in time or an instant in its work volume, it's going to change. Okay? It's going to be different depending upon where we are in the work volume. So no matter what the joint velocities are, the joint velocities can be the same here, here, and here, but because I'm in different parts of my workspace, the endpoint velocity is going to be different. It's going to vary depending on where we are in space. We're going to take a look at another example that will highlight this particular effect. And we're going to specifically focus in on the notion of a singularity. We've talked about singularities. We're going to take a look at an example and see what that singularity does when we're talking about a robot. And the example I'm going to point out, I hope will illustrate the fact that when you get to a singularity, some joint is going to go berserk. Okay? It's going to go crazy, and it's going to cause you problems. It's going to either cause problems with your bearings, or it's going to cause problems with overloads. It will cause problems somewhere along the way. Always avoid singularities if a singularity exists in your workspace. So let's go a little step further and actually come up with this notion of a singularity. So if we're solving these instantaneous kinematic equations, if I have an end effector velocity, which we're going to call p dot. Remember p dot, the upper three elements are essentially x. And the lower three elements are the small differential changes, small angular changes. And so, but this is going to be a 6 by 1. And we have joint velocities q dot. And how many elements are in q dot? Well, that depends how many joints we have. If we have 4 joints, they're going to be 4 q's. 3 q's for 3 joints, and so on. And q can be a revolute joint or prismatic joint. So if we solve p dot is going to be equal to j, the matrix j times q dot, and we're going to assume that p dot is simply a 6 by 1 vector, which I've discussed. Q dot over here could be a 6 by 1 if it's a 6-jointed machine. And if it's a 6-jointed machine, we get a Jacobian of 6 by 6, which is a square matrix. Square matrices are so much easier to deal with when trying to calculate inverse. But the bottom line is, if the determinant of the Jacobian, and I don't want to go back and remind you what determinants are, but if the determinant of a Jacobian, it better not be equal to 0. because of the determinant of the Jacobian, we're going to have problems with the inverse of the inverse of that j. Because why is the inverse of the j important? Because if I have an equation p dot equals j times q dot, then I should be able to pre-multiply both sides of the equation by the inverse of the Jacobian to give me this. But this is only going to work at locations in the world where that inverse of the Jacobian exists. And what that really means is that there is a unique solution at every point in the workspace. If there is an inverse, that means there's a unique solution. But if the determinant of j equals 0, we're going to take a look at a simple example shortly, then there is no j inverse. If there's any place in the workspace, remember j changes depending where I am in the workspace, different values of theta, different values of d, etc. At any location in the workspace, if the determinant of the Jacobian is 0, then there is no inverse of the Jacobian at that particular location. And I don't want to get into all the math. One of the things I try to avoid is make this a course in mathematics. I'm much more interested in your understanding intuitively what these things mean. But essentially, what this is telling us is that we cannot calculate every possible variation of the p out there, and there are going to be locations where there's an inverse, and that means think about dividing by 0. It just goes off to infinity, and those are bad places. You don't want to move your robot around singularities. Okay, so anytime the determinant of j is equal to 0, that particular configuration is called a singular or singularity. All right? Avoid them by all means. And that's why some companies have developed, 8-jointed robots and 7-jointed robots, just added joints to get rid of some of these singularities. Is that really the solution to this? No, I don't think so. It just adds more complexity, more cost, more expense. You don't need to do that. You can simply avoid singularities by staying away from those configurations. And I'm sure on the UR5, you've already experienced its singularities in multiple locations. So move your application around, or make sure you don't move from one point in its workspace to another point in its workspace and going through a singularity. I'm hoping you've identified and figured out what its singularities are, and you've learned to stay away from those configurations. There's no reason in anything you're doing in this lab for you to move through a singularity. None. Okay, so just keep that in mind as you do your lab projects, which are in lab 4. You may end up with a bunch of singularities, but just stay away from them. By now, you should have learned something. So don't waste your time by going through singularities. We're going to take a look at a very simple 2-degree of freedom planar arm. Okay? The reason we're going to look at it is because you can see some of the results pretty easily and quickly. So let's just translate everything we've talked about now to a 2-jointed, very simple, only motion in the plane is allowed. Okay? There are 2 revolute joints, theta 1, theta 2. You can see them right here. The endpoint is E, somewhere in the end effector, depending on what the application is. And ultimately, there is a vector v sub x and v sub y, which is essentially the 2 components of the velocity at point E. And so what we're basically saying is the magnitude, the length from 0 to 1, we're going to call that 1, length 1. That's very straightforward. And we're going to basically call the length from O1 to E also equal to 1. There's no point throwing in an L1 and L2. Just makes our life more complicated. The Jacobian of this two-dimensional planar robot is very straightforward. I'm not going to do the calculations because in your textbook, no matter if you're using the 89 edition or the 2006 edition or the 2020 edition, it calculates the Jacobian in these textbooks. It's example 5.2.1 in the 89 edition and example 4.5 in the latest editions. So it works it out. This is what the Jacobian looks like. So let's calculate, again, and just very quick calculation of the determinant. And it's relatively straightforward to calculate the determinant because this is such a simple 2 by 2 matrix. It's essentially going to be, we're going to multiply minus s, we're going to basically multiply the elements of the determinant. We're going to get minus s1 c12. We're multiplying this element times this element. Minus s12 times c12. That's this element times this element. So that's these two terms over here. And then we're going to subtract the cross diagonal. So that's minus times minus is plus. So this is going to be plus s12 times c1 plus s12 times c12. This is essentially the determinant right here for this very simple 2 by 2 matrix. You should remember that, at least that from your linear algebra in your freshman year, and maybe even in high school. And so if we do that, whenever we have such a crazy trigonometry equation, there are some simplifications we can do. And so remember, s sub 1, 2 is the sine of joint angle 1 plus joint angle 2. We can basically do some trigonometric simplification, which ends up being sine of theta 1 plus theta 2 minus theta 1, which means that this determinant is equal to sine of theta 2. I'm not going to go through the trigonometry right here, but the determinant of j is equal to the sine of theta 2. That's the sine of this angle over here. There's theta 2. So theta 1 dot, remember what we're doing, theta 1 dot is going to be equal to the inverse of the Jacobian times the velocity vector. And what I'm telling you right now is, given that the determinant is sine of theta 2, when theta 2 is going to be equal to 0, what happens to the sine of theta 2? You know, it goes to 0, okay? Because theta 1 dot is going to be equal to this expression. Essentially, it's going to be c12 times vx. Remember, plus s12 times vy divided by the sine of theta 2. If the sine of theta 2 is equal to 0, we end up with theta 1 dot being infinity. And the same thing, we have the sine of theta 2 in the denominator. So essentially, that's a no-no too. We do not want to have theta 2 equal to 0 or pi, which is 180 degrees. So again, we don't want theta 2 to be, we don't want your arm to be stretched out completely or swung back around on itself for the two angles, because when that happens, we are in deep trouble. Okay? So this is the result. So I just want to take a look at a particular, again, two-jointed machine. And we're going to look at its singularities and what happens. There are two places there are singularities. Remember what we said? When theta 2 is equal to 0 and when theta 2 is equal to 180 degrees. Let's take a look at that. When we're going to basically start off, if we're along this arc over here, the locus of points of singularity are when the robot is completely stretched out. When I'm completely stretched out, what does that mean as far as my ability to move in along a velocity? At that instant in time, I cannot move in that direction. I'm locked. I cannot move. I only allowed to move in one direction. That means along the arc or along a tangent, you might call it. But I can't move in that direction. Essentially, I've lost a degree of freedom at that point. I'm locked. That's one singularity. And that's the trivial singularity. Whenever we have singularities, whatever the robot is, when it's fully stretched out at the bounds of its workspace, stay away from the boundaries of the work zone. You don't want to have your arms stretched out because that's not a good place to do any activity because you're limited in some directions. But let's look at the other singularity. Remember what we said, the another singularity is when theta 2 is equal, either stretched out theta 2 is 0, or theta 2 is 180 degrees. That means it's all swung back on itself. So let's look at what happens. Here I have a robot. I want to move from A to B. And let's say I want to move to the singular position, which is over here. And then I want to move straight up to C and to D. Think about that for a moment. I want to move along a straight line. Moving from A to B is no big deal. Okay? No problem. But what happens as I get closer and closer to this position? If I just want to move straight through, not a big deal. Okay? I can, along certain directions, I can still move. But what happens at singularity, I cannot move up in this direction at that moment in time, because what does that require? It requires that this joint angle, this theta 1, has to swing around instantaneously to this position, so this endpoint, which is here, can move up to C. That has to happen in really small delta t's. What that basically means, I'm moving at infinite velocity at that point for me to be able to swing around so that I can continue my trajectory in a vertical direction. Once I'm at C, no problem moving to D. But when I get closer and closer to this position, even if my B is over here, even if I don't go right through the singularity, the closer I get to the singularity, the larger the velocity of joint angle 1 has to be to continue whatever motion I'm doing. Think about the UR5 if you've ever moved the endpoint somewhere over the z-axis, the original z-axis of that robot. It goes per plunk, and essentially it's because the velocities are high enough that it causes the bearings to get kind of stressed out. So let's take a look at what that means if we were going to plot theta 1 dot and theta 2 dot as I move from A to B to C to D. What's going to happen, the motion of theta 2 dot is this motion over here. Not a big deal. But theta 1 dot, which is this first joint, at some location between B and C, it's going to go crazy. Theta 1 dot is going to get very high the closer we get to the singularity. And in fact, I've drawn it as if it actually has a limit. I mean, in reality, it's always going to have a limit because the motor can't go that fast. It's just going to get stuck. But what does that mean in a practical sense? Think about the power. Remember, at each joint, what is the power at that joint? What is the load at that joint? Power is torque times angular velocity. If I max out, if my angular velocity gets to be very high, my power, my load, is going to get super high, and the motor is going to stall out. Stalling motors is not a good thing. Okay, you want to avoid that condition. And typically before it stalls out, the bearings are going to go crazy, and they're going to, you might damage your bearings. So again, stay away from singularities. This kind of just shows you this issue of one velocity for theta 1 is just going to get extremely high. That means very high power load requirements. And so it's going to cause all sorts of issues. So avoid singularities. And so if we take a look at, we've looked at this revolute joint a few different times. If you remember, the Puma robot had this particular configuration: forearm rotate, wrist rotate, and then tool rotate. That is essentially this spherical wrist singularity. Here, think of this as the forearm rotate. Think of this as the wrist rotate and the final tool rotate. Okay? This is a spherical wrist singularity. And what happens is when these two degrees of freedom, theta 1 and theta 3, line up, this machine is going to lock up, and you cannot move in the opposite direction. So, in other words, you can't even do a compute. Let's say theta 1 is some particular value. What that basically says, this theta 3 can be any value up here. That doesn't, but the key issues at the singularity, this is going to, because you cannot move normal. So if this is, let me consider upper arm rotate, forearm rotate. So let me make this a spherical wrist singularity. When I completely lock up, I can rotate forearm and lower arm. If I do that, notice there's an infinite number of solutions at that position. I can have this be at one angle and this be another angle, and still, how do I compute that? You can't. It's a singular condition, and given this is my elbow joint, but think of it as a wrist joint. When I'm fully like this, I cannot rotate normal to the axis of that wrist joint. So if this is the wrist joint, I cannot. There's no way I can move. I've locked out. I've eliminated 1 degree of freedom for my robot during that singularity. Questions? I'm going to stop here. The next subject I'm going to talk about, which is I'm going to talk about on Thursday after a review of the exam, is going to look at how this Jacobian plays a role in force calculations. It's going to be very important for being able to calculate what are the force relationship between the torques in the joints and the final forces at the end effector. And we're going to take a look at an example of a load cell, a 6 degree of freedom force sensor. And you'll see that the analysis of that force sensor, that Jacobian, we're going to be dealing with the transpose of the Jacobian. Till now we've talked about the inverse of the Jacobian, but we're going to talk about the transpose and how it relates the forces and torques at the end effector with the individual forces and torques in each individual joint. So that will be Thursday. I know how very excited you are to move on to the next subject. All right, thank you. Have a warm rest of your day, and don't get stuck in the snow. All right. Warm rest of the day.
Now, we can enjoy the rest of our Tuesday. What? 22. It's Tuesday.